except in this instance, the three-particle problem not only has a one-dimensional kinetic energy, but it also has a potential energy. The potential energy has a value which I call A. So I want you to solve, write down the quantum mechanical Hamiltonian. In other words, you're going to go through that solving a quantum system process. So you'll write the quantum mechanical Hamiltonian, you'll put it into the Schrodinger equation, the stationary state version, solve the quantum system, produce a total wave function in terms of the mass and other constants, given that the energy of the particle is greater than the potential. For So for the potential energy you have here, the energy of the particle for this part B is higher than that energy there. Okay? Higher than that potential. Then, produce an expression for the energy of the system. Go ahead and do that. Repeat B and C. Now, you'll have an energy of the particle incident from x equals 0 less than that of potential. You'll say, how can you do that? Well, it's quantum mechanics now. Quantum mechanics is not classical mechanics, so the wave function can exist in that region. I want to like to know what that wave function is and what the energies are for that as well. So just a free particle problem all over again, except now you have a potential, and whether the energy is greater than or less than A goes to how you solve the differential equations. I think we're just gave it away right there. See if you're paying attention to the central. Then finally, when you consider the first postulate, now are there any conclusions? Because you remember that when you still, it's always a second order differential equation because the Hamiltonian, the kinetic energy term, is a second order differential equation. So we always solve the system and we're going to have two constants of integration. And postulates of quantum mechanics can allow, disallow, conditions of the problem can allow, disallow those particular constants. So it's just having you to examine those, and it's a logic question within there. And then another probability problem. This problem follows 10.2 that you did in the homework, and so it goes in this way. Chlorine has, as you know, two common isotopes, 35 and 37, with percent abundances that are provided there. You wish to synthesize a boron trichloride molecule having designated isotopic fractions. So the problem then proceeds as in that, except there's a couple of points to make on this. If BaCl3 is synthesized in the gas phase, what would be the probability of having molecules of the form B with the 35 chlorine, you have three of them, so the boron with 335 isotopes, a boron with 235 isotopes and 137, 135, 237s, and also 337s, okay? Now, I could ask this question in another way. I said, all right, if we did a mass spectrum of this thing, how many peaks would you see, and what would be the heights of the peaks? All right? That's what this is going to. So I give you a hint because I'm amazing. As I said, to show the probabilities are normalized, so that's a clue right there. If you get it right, you should have a normalized probability. So hint and note. I will point out that there are three possible arrangements of boron 35, chlorine 2, 37, because you could have, you have three different chlorines. Chlorine number 1 could be 37, chlorine number 2 could be the 37, chlorine number 3 could be the 37. You have those permutations. You got to keep that in mind. And then also, there's only one each, of course, of the borane with the 3 chlorine 35s and 3 chlorine 37s. Also, for one boron and 3 chlorines in the molecule, you have a probability, and these were words that were left off when I put it out on the web, or actually in the Dropbox. I left it off, the sentence ended here. But you have a probability that includes 4 elements. That's boron, chlorine number 1, chlorine number 2, and chlorine number 3. That's 4 elements, so you have to think about your probability combinations. That's what goes to that particular type of problem. Is that all right? Straightforward? I figured. Never mind. Okay. Any questions on that? All right, then going down the elements, let me ask you this. First minute of the first day, how do you calculate an average? So I have a probability function. I'll call it probability as a function of x. All right? How do you calculate an average x? How do you calculate an average x? God, I'll change your majors.
It's multiplied by a fraction. It's probability
That is the
multiplied.
fraction.
Yeah.
So that the probability is the fraction. So how do I find now average x using that probability? We'll presume it's continuous. Okay? Over all space, right? All space is a variable term. It could be, for a periodic system, it could be 0 to 2 pi. If I have a limited system of a certain distance, it could be that 0 to that distance. I could have all space 0 to infinity. But that's going to vary with the problem. So I'll just say in general all space. What do I put in under the integral sign? This is amazing.
Probability times the function.
Okay, say again.
The probability times the function.
So the function being specifically whatever's in here. Correct. So whatever's in here goes here, multiplied by that probability function. Since it's a continuous system, it's dx. If it is a discontinuous system, that becomes a sum. It's the only difference. Same thing applies. Okay? Now, how do you find, now you have psi, how do you find the average for a quantum system? What's that? Almost. I'll start you off. Yep. If you did this, what you're claiming here, what are you going to get? 1. So I'm asking for an average, not normalized probability. It works the same as this, except that, and what Carly kind of points out inadvertently, this is a probability. So psi star psi replaces your classical probability term here. The only difference is we're working instead of with a particular value or a scalar value, we're working with operators. So the way it's done in quantum mechanics is you put the operator, so we usually designate that with a little vertical hash on there, times the wave function. So you have, there's psi star psi is your probability, but whatever I'm asking for here, you put the operator for that there. So if I were asking for the average momentum, I would put this integral again over all space, psi star, momentum operator, times psi. And where the momentum operator in quantum mechanics is minus I h bar ddx. So everything we have, a position, a momentum, an energy, a potential, a kinetic energy, a rotational energy, an angular momentum, every quantity that is a corollary in classical mechanics has a quantum mechanical operator associated with it. To find the average, you sandwich it between there, and the order of operations matters. You operate to the right, you then multiply by the complex conjugate. If the wave function happens to be real, then there is no complex conjugate. You just multiply by another one. Then integrate. It has to be in that order. So that's how the averages differ from classical systems to quantum systems. So I wanted to make that point in there. Because we started off then with, we're done with this, with obviously probability distribution. Again, I want to apologize for the homework problem where I used an origin shift in here. I will fix that for future classes. Because it confused a couple of people. Because it was where I started from 1 to 8. And so I get a little bit of a red face and apology on that. So here we started with just numbers. No functions, no probability functions. We had to build them. So to build this, I said, what are all the possible values? In this case, it was 34. So the probability is the value divided by the all possible. Of course, you did rods and lengths, and you did a couple of problems associated with that. Okay? And then we said, well, what's the probability of having a value greater than 5? Then you sum up the probabilities. So that, in other words, this is a question. The probability of having a shot put or growth greater than 5 is an and question. That means what's the probability of having a 6? Actually, it's an or question, excuse me. A 6 or 7 or 8. So when you use the word or, you add them together. So what if I said, what would be the probability of pulling from my pool of candidates someone that can throw 5 yards and 8 yards? Then we have the probability for 5, probability for 8, just hit and multiply, okay? But once those probabilities are normalized, then you can do it in that way. So then we did the average, exactly what I've indicated here. The average is the probability times whatever value that you're interested in. Average square in this instance, the probability times the average squared, which of course we used to produce this quantity here, which was the average square deviation. So you take the distance from the average, or difference from the average, square it, multiply it by that probability. The reason why I introduced this here is because you have seen now that this is what we call in quantum mechanics the uncertainty. So we do that as uncertainty equals. So where's the particle? Well, it is here with this uncertainty in there. So we developed that. Well, then I just kind of made mentions of standard deviations and a couple of different things. Did a couple of samples on that. And here's where our or and type of possibilities. I had a donor that can give either A positive or AB positive. So what are the probabilities? Well, it's the A positive probability plus the AB positive, so there's our total probability. Well, then we had a second donor, and I said, well, we have to have a second one that has to be able to donate as well. So the probability of 1 multiplied by probability of 2. So now that is an and. Remember, or and and, keep those in place. We'll be using those later. And then I did a couple examples on that. And then finally, we went to what if we have, a discrete data, can I represent it as a function? This is a discontinuous function, okay? Discontinuous function because i's are integrals. These correlate now to quantum numbers. We're gonna have quantum systems that look like this. And we're gonna have to decide, can I treat this as an integral or do I have to treat it with a sum? So we had to know how to do both. So in this instance, we will have to do that. So we have the sums, everything goes into play, like square distances and everything along that. And then we, again, what if it were now continuous? So now we did an integral, we're presuming x to be now continuous. Now you can have not just 1 yard, but 1.001 yard, 1.002 yards, or whatever you want. All the way up to 8 possible yards. Now we do integration. When we looked at the final numbers, and of course we did a normalization on that. When we did the final numbers, we saw that they were a little off. So here's the previously calculated values, probabilities, and the problem. Why were these off? Why were they different than the discrete values? Fundamental rule of calculus. And essentially, it's correct. If we say, okay, I'm going to be nitpicky here. I remember being nitpicky is a good thing. If it is, I say, well, it's discontinuous, end of story. All right? But remember what calculus says, is that if you're going to do, a function, and you're going to integrate it, what calculus does is break it up in these intervals, and then calculate these squares in here. So that's a discontinuous function, exactly as you point out. If it is still discontinuous, but these squares are teeny, 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 tiny, then you lose that error. So these squares in here were too big to do an integral on it, but they weren't too bad. So that's a decision we're going to have to find. When we get past this exam, start looking at translation, rotation, and vibration, we're going to make those decisions at each point. All right, so that was engaging probabilities, obviously an important topic because you're beginning to see. We then turned to classical mechanics, and first off, I introduced the 3 differential equations to be able to solve. One, they were all second order just for, but this applies to first order in this instance. where I have second order, two derivatives of y with x squared and a constant, just a constant by itself. This can be done by separation of variables, and we did that in the Newton's equation problem. We solved that case. So we solved the equations in there. And that is, of course, every differential equation, when we solve it, we're solving it in general. We produce two constants of integration. Those are determined in classical mechanics by initial conditions, quantum mechanics by boundary condition. Terminologies are slightly different, but the objective is still the same. So then we turn to differential equation number 2. Point to be made, again, very, 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 very important. To give you the example again. Hint, hint, hint. This K must be positive. K, the constant in there, must be positive. If this K is not positive, that turns this negative sign into a positive sign and changes the solutions. Okay? Got that down? Been tattooed in your brain? I guarantee you you're going to need this. So if we have a negative sign, then we have real solutions. We have exponentially, there's no complex, there's no I within them. Notice that the K turns into square root K. That's when we actually solve this for our quantum systems. We have this. I'll say, which one do we have here? Let's see. Let me go ahead and do this. Minus K, I called it K squared. I equal to 0. I made that arbitrarily. This was 2me over h bar squared when we did our quantum systems. I called it K squared for convenience only, so that when I had this square, it would just turn into K there. It would have worked either way. If I just called this K, it would still work. We had the square root, numbers would come out identical. But it was just a matter of mathematical convenience. But you have a second derivative, negative sign, constant times a wave function of the function again. You simply write down the answer as real exponents. Once again, two indeterminate constants which we evaluate by boundary or initial conditions. Then if you have a positive sign, you have one of two options. The two options are, you can have it as cosine plus sine with their general solution and the undetermined coefficients, or you can have complex. As I just pointed out, complex exponents are oscillatory. They are sines and cosines. Okay? So that is then the case within there. And then the choice of using these is of convenience. When we did the free particle problem, I chose this because we could interpret this root K, well, R ended up being Kx, as being momentum. So we had a particle that was incident from left to right, and particle from right to left, and we associated this positive I root Kx as a particle with a positive momentum, negative root Kx is positive with a negative momentum. We will find when we look at our first system when we come back, that where we have, I will bound my system. When I bound my system, this will be convenient. Both will work. Both will work. One will just take you more effort than the other. It's the only difference. You have, otherwise you can get identical results. All right, so that was generally that. So then we turned our attention to classical mechanics, some general things to know, the postulates, which are no great big deal. But we wanted to solve quantum systems, or classical systems, which we will do. Please take note of these little energy conditions, that if you have a potential energy, for example, mgy, the gravitational potential energy, you take the negative of the derivative with respect to position, you get then the force. So dV, negative dV with regard to position is a force, and the momentum is the derivative of the kinetic energy with respect to velocity. We'll see that again in a moment in Hampton's equations. So I just did a different force pop. So these are just simple energetics to be useful to know. Then I introduced the equations of motion. These are the Newton's equations of motion. These are only good in Cartesian systems, but they are easily solved. And we did do that. The Newton's equations are, we have a mass, then times an acceleration, essentially. So mass times d2x dt squared, plus dv dx, that's also a negative force, which we just saw, which adds to 0. Since mass times acceleration is a force, minus dv dx is a force, they obviously add up to 0. That's where that was deduced. So then we just did just a simple mechanical system, did a cannonball problem. You kind of did a similar one where I gave you potential in the x and y axis. So just be familiar with it. I'm not going to have you redo a big, classical problem, but I may have you do a small element of it or something, or extend from what you had done. But then I introduced Hamilton's equation, because Hamilton's equations can be used in multiple coordinate systems, which we will see. Here's the important thing to know. These are Hamilton's equations of motion. It says, first you write down the Hamiltonian, which is kinetic energy plus potential energy. If this is a classical particle, for a classical particle, the kinetic energy is p squared over twice the mass, which is equivalent to 1/2 mv squared. But because the Hamiltonian has to take a derivative with respect to momentum, we have to express the kinetic energy in terms of momentum. Okay? So one particle, one dimension, one term. One particle, 3 dimensions, 3 terms. 2 particles, 3 dimensions, 6 terms, so forth and so on. So this, and then you will have some potential energy, which is usually, or most often, a function of distance. That's what potential energy really is. So this is then, now this becomes the Hamiltonian classical. We turn to the Hamilton's equation of motion. The derivative of the Hamiltonian, so if I take this derivative with respect to momentum, I get the derivative of position with time, which obviously is the velocity. So derivative of momentum is the velocity. The derivative of the Hamiltonian with position, which is usually here, except in the spherical system, you get an additional term. But derivative of this with position will give you dp dt, which is a force. Okay? Derivative of this gives you a force. Derivative of this gives you a velocity. Then we have 2 differential equations, both single order, so we only have to do 1 integration each. You still have to do 2 integrations, but then you just have to. But we're applying those in quantum mechanics in a slightly different way, but knowing what these are and what those terms mean will be the most important part that I will be asking upon. Then I just simply redid the cannonball problem using Hamilton's equation. We got exactly the same results. But then we had to turn, because we wanted to now begin to go into the quantum mechanics, but I had to introduce the Bohr model for the hydrogen atom. So I had to convert the Hamiltonian into angular or spherical coordinates. We did just simply plain polar, because that was sufficient for us. It was simple enough to do. I'm not going to have you redo this. I'm not going to have you work with that, nor, but I will present this to you if you need. But we just ended up now with the Hamiltonian. Here is the radial kinetic energy. There's the angular kinetic energy. Note, there's an R down here that affects how we take our derivatives. And then, of course, whatever potential. So that's Hamilton's equations of motion in spherical systems. They're plain polar. If I do have 3-dimensional sphere, there's going to be a 3rd term, but everything else still applies. Nothing really changes on there, except we just have a 3rd term. Yes?
When you say potential energy is constant, what does that mean? Constant throughout the entire system within boundary conditions?
Are you talking about the web exam?
Yeah.
For the web exam, I said you have a uniform potential energy that goes to infinity and never changes.
So it is 0 to infinity?
If I had done this, and I could give you a potential that looks like that. Now that potential energy is varying with position. Okay? When we saw the Coulomb's potential, then the potential energy of that looked like this. So as it got closer to the nucleus, the potential energy went down. That means that it's varying with distance. All right? Whereas saying constant is exactly that.
Just 1.
Mm-hmm. And we will stay with this until the potential does this. It varies, oscillates in time as well as space. Okay? So just keep in mind, so we're not going to get to that until we get to spectroscopy near the end.
So the potential energy in the web exam is not a function?
The little voice we can have one.
The potential energy in the web exam is not a function of anything? It's
Just a constant. That's correct.
So like when we set up the Hamiltonian, it should be
6
plus A.
plus A. That's it. Not A over R. Not AR, not AR squared. Just A. Okay. So I'm asking you, I would give you this, ask me to ask you to toy with it, but I'm not gonna have you derive or actually have you memorize that in any way, shape, or form. So then we in spherical coordinates, here's Hamilton's equations of motion. Once again, the derivative of the momentum term with respect to time is the minus dv d theta, that's the force in theta. With r in time, that's the force radially. And the velocity theta and velocity r are the derivative with respect to momentum respectively. So those are the things to pin on those two derivatives that you take. Then we went to the Bohr model. And the most important thing to know here, now here we're talking about failures of classical physics. Okay, I'd like you to just be familiar with those. So what are the failures of classical physics? And also, what did Bohr do to come up with so much of the right answer? Where did he get that idea from? Well, what he did were these things. The exception of classical mechanics holds, potential force is Coulombic, that's no surprise. That's classical physics right here. But he said electrons rotate around the nucleus, but they do not spiral in. They're in fixed orbits. Okay? Violation, throw the penalty. And he said here, the angular momentum is in integer multiples of h bar. H bar, of course, being h over 2 pi. Where does 2 pi come from?
Circle.
We're working in circles. That's right. So Planck's constant, where did that come from? Or initially, do you remember? Was that, if you say Planck, it's 5 years.
It came from hydrogen, right?
Einstein used it. You're right. It was actually, I'm going to kind of qualify what I was about to give as my answer. I think it was simultaneously Max Planck and Albert Einstein. Planck initially, I think, produced it because he was looking at, things that glow when you heat them. And that they had, the physics couldn't reproduce that. But he said, all right, molecules can only vibrate certain ways, quantized, okay? Einstein kind of jumped on that at about the same time because he was, I understand, a fairly bright guy. And he used that for light, okay? So he was finding some relationship. Planck was finding those relationships. So you could probably call that a Newton-Leibniz equivalency, Newton invented calculus, Leibniz invented calculus, and they argued actually invented it. Which is kind of one of those, it was time for that thing. And so the Planck and Einstein were probably simultaneously the ones that produced that. So anyway, so de Broglie jumped on that, and he had this angular momentum. He was spurred on by doing this because of atomic line spectra. Since you don't get a continuous spectrum, you get lines. He said, well, they have to be in fixed orbits. And so he did that. But the Planck's constant, so he was actually quite clever. So he produced that. He then used Hamilton's equations in spherical systems. I did it, of course, in plane polar system. So here the plane polar Hamiltonian plus potential energy, which was, of course, Coulombic. He then said, all right, there is no radial momentum because the things are fixed. They're in a fixed orbit. So he set that equal to 0. And he said, well, when you say, what is the acceleration in the r direction, he set that equal to 0 as well. Because it said fixed orbit, and he's not going anywhere. So he then used Hamilton's equation, collected everything down, produced what is now known as the Bohr radius, which turned out to be exactly right. And he then went down and found out what the energy should be. He then computed those energies and compared them to line spectra, and it was just a little bit off. Why was it a little bit off? Remember? Close.
There's no mobility for position. It's not a fixed position.
He said in that derivation that this is nailed in place, does not move. We now know that there is a very slight, so there is kind of in Bohr's model, kind of an oscillation. So when you replace the mass of electron with the reduced mass, which is mass of the electron, mass of proton, mass of electron plus mass of proton, when you replace that with the reduced mass, Those numbers then get adjusted, and they get pretty much nailed spot on down to 2 digits past the decimal in angstroms. And the remaining elements of these come to now quantum mechanics, which you did not know. So he nailed the radius, but he had a lot of things wrong. He said it's a particle in an orbit, wrong answer. It's a quantum cloud, right? Secondly, he had no idea about orbitals. So the periodic chart in its form had not come about. He could not explain the periodic chart yet. He didn't know about p orbitals and s orbitals. He didn't know about magnetic quantum numbers and spin and all that. So, but it was still a tremendous success. Well, then here's the black body radiation for where Planck came from. Here is then this is the hitting light onto a metal and ejecting electrons, where Einstein was able to produce a relationship between the Planck's constant there. So those were kind of the failures of classical physics within there. So that finished us off there. And then we went through a highly conceptual chapter, or section of the chapter. All these are in chapter 12. The first avenue on this, again, it's really funny because all these different things are all coming about at the same time. Did I ever show you that picture of the Solvay conference? You really need to see this. It kind of goes to where, I think I have it here. This is 1927. It's a conference. Oh, shut up. Play it. Nothing wrong with that. Open with. I'm gonna open this. There you go. Let's try with the head. That one. Let's try this. There you go. All right. Check this out. This is a single group photo. Look at the names. You have Henrietta Ehrenfest had a lot of information with this, but just look at, here's Erwin Schrödinger, the wave equation. Here's Wolfgang Pauli, Pauli exclusion principle. Werner Heisenberg, Heisenberg uncertainty principle. Brilliant zones for crystals. You have Knudsen, we talked about Knudsen formula, Newton's expansion. Peter Debye, Bragg diffraction. P.M. Dirac, we're probably one of the brightest guys in that whole group, if you can imagine, he's brilliant. Compton and Compton scattering. Louis de Broglie, you have the Broglie relationship to the wave. Born Oppenheimer, Niels Bohr, Langmuir, Planck, Max Planck, Marie Curie before she just utterly died, Einstein, Langevin, Wilson, Richard. I always think if someone had dropped a bomb on this, when this photo was being taken, it would have set back physics for 500 years. I mean, just the brains in there. But it goes to show that all this stuff is developed really almost simultaneously. Once they kind of related themselves to wave theory, did that. So it's my favorite photo. I got actually a poster of that at home. All right, so where was I? Oh, yes. So here we just said the momentum is by de Broglie, Planck's constant of the wavelength. Value of Planck's constant is why we hadn't seen quantum effects till we got down to the 1900s, because it is 10 to the minus 34th. If you're 10 to the minus third, quantum effects would be normal for us. So I just compared that. So I said I have an electron. So an electron has a predicted de Broglie wavelength of about 7 nanometers, which is eminently measurable. But if I do it to a BB, it has a wavelength of 10 to the minus 24th nanometer, so it doesn't behave like a wave at all. So you don't get those properties. So that's the Planck's constant is considered where the threshold where quantum mechanics begins. So and then I gave you a hand-waving argument of the development. You can simply produce that, and just knowing what that is will be fine. Quantum mechanics, classical quantum the consequences of these things are worth knowing. But if you know the forces, where and how fast, you know everything there is to know. You know how everything will be, in however you want it done. And you know everything there is to know about that. Quantum mechanically, it is in a wave function. You have to get this. In this, there's everything that you need to know. It's just kind of harder to get it out. You have to do all these averages and things like that. Energy is continuous. Quantities are quantized. Here we have the uncertainty principle, where you can know position and momentum precisely at any known time to any degree of exactness. Whereas quantum mechanics, you can't. You're limited. You know one, you don't know the other. The more you know one, the less you know about the other. And I demonstrated that. And here we go, delocalization, we will get to all that. Tunneling, we will get to all that. But I just demonstrated that position momentum when I did this uncertainty principle, and I took a whole bunch of waves, where I didn't know what the momentum of the waves were, but I know they were between here and here. And I took all those waves with all those momentum, I combined them to an overall, so you got constructive and destructive interference. And so where a particle, we know where it was, we now know a little bit more where it was. So the less I know about its momentum, that's the second term here, the more I know about its position. So I release my knowledge on the momentum, and the particle gets more localized. So they're inversely proportional, and that leads to then the Heisenberg uncertainty principle. And here's that relationship I pointed out earlier when we were looking at classical mechanics as the average deviation. But now in here, what's called the uncertainty, and Heisenberg demonstrated that the uncertainty in x and the momentum is always greater than and equal to h bar O2. We know any two variables, whether they fall under this or not, whether the variables, the operators for those variables commute. We got into operators. So if I go to the quantum mechanic operator for position, quantum mechanical operator for momentum, do a commutator on those. If it is non-zero, they do not commute, and this holds. If they are zero, then I can know one and the other to precision, to any degree of precision that I like. So these are complementary variables within there. So this is going to kind of bite us in the butt a little bit later, but we'll need it. And then we just did a little bit of operator algebra. The algebraic rules in addition are simple, so obviously that goes to subtraction. Addition and subtraction, any combination of operators on a function will give you the operator, the values that produced by that function. But the commutators were important significantly because, as I just mentioned, if I have two operators, and we know operators are associated with things we measure, position, momentum, negative momentum, if two operators, when do not commute, then the Heisenberg uncertainty principle holds. So we write a commutator. The general notation is I have a bracket F comma G for the two operators, and to find the commutator, you take F that is operating on G, which is operated on X. Then you do G, that's operating on F, that's operating on F. You do them in reverse, subtract the two results. And you should be able to do this in general, Mark. Now, you used a specific function, but you should be able to do that in general.
I don't know how you do it in function.
Okay. Let's do that. What was the one that I had? I had T and DDT. Or was it, what was the one I had at home? I'll show you that.
Oh, this, right.
Yeah, but you put a function in there. I was going to show you how to do it in general.
Okay, it was second derivative and then x.
So,
Bracket.
second derivative then x. So I had one that was d2 dx squared, and then I had an x, right? Okay, this is how you do it. You just pick something. I just call it f. That's my function. All right, to do this, you first operate on f by x. Well, that x operator is just a multiplication. So this is x operating on f. So this says now take two derivatives of this. Well, this is a product function now. Okay, we'll go this on that one. Product function, so it's the first x. Don't know if I'm going to do this way. So this would be equal d dx of the first x times the derivative of f, which is df dx. See, I didn't have to have a function, I'm just going to represent it in that way. Plus f times the derivative of x, which is just 1. So that's the first derivative in there. The second one is, again, I take d dx of this, I have the first times the derivative of the second, which is d2f dx squared, plus the second df dx times the derivative of the first, which is just 1, now plus df dx. So this answer comes out to be x d2f dx squared plus 2 df dx. Now if I do it in reverse, where I have x times d2f dx squared, Well, that's an answer that's already there. So first I take the second derivative, well, that's it. Then multiply by x, well, there's the answer. So here's the first order, here's the second order, but these two are the same. So your commutator turned out to be that. That's how you do it, just putting a general term in place. Okay. So your answer was correct, but in general, you probably want to have a kind of a general answer on that.
So if you had a function, it would be where f is.
Correct. Which is exactly what Carla did, just because she worked it from the inside out. Which again is correct. Right, so commutators are important to the knowledge of what things commute and how to establish if they commute. Then we have eigenvalue equations. These are a product. An eigenvalue equation, specifically, a couple people got this one off, is an operator operating on a function. You get a constant, not a value of x, not a value of theta, a constant. Multiply that function back again, okay? So it cannot be a function. So if I say, if I have a function, I said is x squared an eigenfunction of this operator?
No.
Well, you do that, this times x squared, you get 2x, right? And that's it. So I get, back this, I get 2, but that's not my function back again, okay? So it's going to be things like exponentials, sines and cosines, stuff like that, rather than that. But it has to be a constant and return a function. So keep that in mind. Don't want you to make those errors. So that's indicated, and then of course I gave you a couple examples, and the most important element of it is to recognize what defines being Hermitian and what the significance of being Hermitian is. Hermitian operators guarantee two things. They guarantee that when we do have an eigenvalue equation, the constant that we get will be a real number. So when we have this at the Hermitian, if I get a momentum value, it'll be a real, it will be a complex number. Secondly, and these we will see going forward, particularly in almost the beginning of the next chapter, the two functions are properly orthogonal. What that means is if I have two answers, psi n and psi m, that are both solutions to the Schrodinger equation. If I did this, that's equal to 0. Okay? So if this function is different than this function, usually what that will mean will have a different eigenvalue, or I'm sorry, a different quantum number. Like you'll have a cosine 1x and a cosine 2x. If you take an integral of cosine 1x and cosine 2x, you find that it will always go to 0. So we can be guaranteed that, which will be very, very advantageous. In Bra-Ket notation, it says that psi of g on phi is equal to then g psi on phi. Keep in mind, if g here is, like, for example, minus I h bar ddx, the momentum operator, once you put it to the other side of that line, this becomes the complex conjugate of it, of plus I h bar ddx. So this first vertical line means everything to the left of it is a complex conjugate. So if the operator is complex, then when you put it over on this side, you change it. Remember, to make a complex conjugate, you turn every I into a negative I, you turn every negative I into a positive I. Okay? And then that will be guaranteed those two things will be suitable, and that will be tremendously advantageous to us. So we're just kind of going down through these details. Then I had the postulates. These operators I will probably give you if you need them. We'll see them enough that you'll eventually know them, but I'm not going to worry about you actually memorizing. Please know first postulate and what functions might look like if they are discontinuous, because a wave function must be continuous, finite, single value. There's also another called square integral that where it comes into play. I'll make a point on this. I'm not going to share about this. A discontinuous function. Here's an example of discontinuous function. Right? So when it goes to this side, it only appears here. That's a discontinuity. This is also a discontinuity. You have a customer. That's a discontinuity. Okay? Because it has a slope up and suddenly a slope down. Okay? So to be continuous, the value has to be the same and the slope has to be the same. That's a definition of continuity. So when you look at functions, if you see a break in it, like something like this, if you see a break in it, that's discontinuous. Okay, so keep that in mind. You have to have that.
So if it breaks the first postulate, it's not permanent and resolved. What does it mean when it breaks the postulates?
Yeah, these all violate the first postulate.
Okay, so if it violates that, it's just not a quantum mechanical.
It's not an allowed solution. So if I have I say, all right, the first term violates the postulates. Because depending on how it's defined. If I said this is defined over a region of 0 to infinity, okay, well, as this goes from 0 to infinity, it gets smaller. As this goes from 0 to infinity, it blows up, making this requiring that to be equal to 0. If I said it went from minus infinity to infinity, then both terms are no good. That's not a solution. Okay? That's what I mean by violating these things. Okay? Please know, okay, the measurement, an eigenvalue equation, which is kind of redundant. If you have an eigenvalue equation, this answer will be something you can go in and measure. That's what means physically measurable. Okay? And please know how to, when I walked in, one of the first questions I asked again is how do you calculate an average and how do you normalize? To normalize, you integrate over all space, whatever that space is defined to be. Psi star psi is set equal to 1. We produce a normalization constant. It occurs in classical statistics as well as quantum statistics. Then to find an average value, just like I mentioned, you sandwich the operator for that value between the psi star and psi and integrate. Technically, you divide by this, but if you've done this step, that denominator will be 1. Okay? Which we can represent as the normalization constant, wherever that is defined in here. So you can normalize, which we will do first all the way. We then did a little separation of variables. I had you do a homework problem on this. I did space and time. You did 2 different spatial coordinates, so be familiar with that. And then we finally solved our first quantum problem. You will solve a couple of them, because we've solved one here, and then of course you're solving for the free particle problem with a potential. In there, so you have an additional one within there. These are the steps, always. These are worth tattooing because they don't change. You write down the system Hamiltonian. That's usually just written down. We understand that a Hamiltonian quantum mechanically is minus h bar squared over 2m second derivative with respect to x squared. If it is an angular system, that becomes I instead, just like you did in your rotational problem. So that's a kinetic energy operator. So if you, once again, if you have 2 particles in 3 dimensions, you're going to have 6 terms. You're going to have 1 of these in each dimension for each particle. Okay? That's typically how that goes. We'll have to kind of see if we can reduce that, because we're going to be looking at diatomic molecules. We'll be having 6 terms and 6 wave functions. And we see how we can kind of bring that down. So we substituted into the Schrodinger equation, stationary state from now, as long as the potential is constant. By the way, when we did our separation of variables, for x and y, you did separation of x and y. When can you not do that? If they're inextricably coupled. So if my potential was x plus y, I'm all right. If my potential was sine of x times y, I'm screwed.
But x times y classifies coupled together straight up?
Yes. That'll be coupled. Because you will have to kind of separate it by some means. That would have to be. Okay? Since these have to be summed together, you won't be able to do that. So multiplying would be an example of that. So you have a substitution. We have then, for the free particle problem, we determined that our k squared from our solution, that A and B, in this particular, it's a unique system because we had no forces on the particle, so I arbitrarily set A and B equal to each other, because A, we will see, because of the orthogonality, will be the probability of having the particle going forward, B, the probability going in reverse. Remember, K is associated with momentum through HK. Okay? Actually, specifically H bar K, so HK is the momentum. So K is not directly the momentum, but it is surrogate for it. The free particle problem, we did a number of things. We demonstrated that the momentum was a value, H bar times K, so there's momentum, so it's measurable within there. Its position is entirely unknown, but this is the only system that was not quantized. Okay? So far. And not quantized because the waves have the restrictions on them. Once we put restrictions on the waves, that will change. Like you saw in the particle and ring problem. Anyway, try to get through them. If you're not sure about it, you might need to know, you're welcome to ask. I'll probably ignore the question.
Now, you said you'll probably give us those postulate operators. Is that?
Yeah, I'll say I will. You would like to, you'll have it at home already.
Yeah. just-
And so then you're going to be doing one of the web exams, and so
Did you say we can't separate any of the poles together?
you would not be able to.
But we don't have. But it won't.
Yeah, what you're going to think about that. You got,
Separated, I think. Did you say? That it is another way to be able to separate it. Why?
The only way to do that is what we see, if we're going to come up with that situation, is you have to pick a new coordinate system. And the coordinate system will solve that problem.